Hi everyone, it's Michael here with some exercise solutions for today's lecture, which would be week 4. In this question we've got a person with a body weight of 700 newtons, and when you see newtons you know that that's a force. Okay, there is a force being exerted here and it is their force on the planet Earth. Okay, if they visited the moon, what would their force on that planet be? Now we've got an equation that relates these, which is F equals ma, okay, and that's not only used for calculating the force on a planet, but if we apply a force to a given mass, we could work out the acceleration, or if a given mass has a given acceleration, we could work out the force that needs to be applied to it, or has been applied to it to get that particular acceleration. For us, our force is 700 newtons. 700 newtons, and that is equal to, I'll just put that in brackets so we know it's a unit, our mass multiplied by our acceleration, and on Earth the acceleration towards the center of the Earth is 9.81 meters per second squared. We should have a direction here, but in this particular question we're finding the mass, and the mass won't have a unit with it. Not a unit, a direction with it. Mass is just a scalar number, so we'll ignore that for the moment. When we want to find our answer, we're going to try and get m by itself, which is after we divide both sides by 9.81 meters per second. So if we do that, we get 700 newtons over 9.81 meters per second squared, right? And that is equal to our mass, except it's very hard to see what's happening with the units here. So I'm going to rewrite 1 newton. 1 newton is equal to 1 kilogram meter per second squared. And if you're not sure how to remember that, look at the formula. The force is equal to mass times acceleration, and in our SI units, our force will be in newtons, our mass will be in kilograms, and our acceleration is in meters per second squared, or 1 newton is equal to 1 kilogram meter per second squared. We can also write it like that. Okay, so I'm just going to change our newton over here to be 700 kilogram meters per second squared divided by 9.81 meters, put it in brackets, meters per second squared. And we can see here most of these units will cancel out. So we'll get our meters will cancel out. Well, actually, I'll change pen color for that. Our meters will cancel out with meters. Our per second squareds will cancel out with each other. If they didn't cancel out, just expand it and work it out individually. We'll be left with kilograms, okay, which is what our mass will be measured in. For our calculation here, let's see. Oh, my calculator's on the other screen. Very easily we'll have 700 divided by 9.81, and that gives us an answer of 71.35. Lost it. 71.35 kilograms is their mass. Now that does not answer our question. Our answer question is what is his body weight, and it's already indicated that body weight is a force, so now we need to find the force on the moon. So using this value that we just found, which is their mass, and their mass doesn't change when they visit the moon. The astronaut still has the same amount of mass until he loses some up there from going on a diet and eating specific foods. But in general, his mass stays the same, or her mass stays the same. So for our final answer, we get the force on the moon is equal to here's their mass, small m of the person multiplied by the acceleration on the moon. Okay. Our force on the moon is what we're looking to find. This is equal to 71.35 kilograms multiplied by our 1.6 meters per second squared on the moon, and that gives us 71.35 and times 1.6. Well, it should be 71.36. I can't round. Multiplied by 1.6 is equal to 114.17. Now, we've been given this in two significant figures, so we'll only quote our answer in two significant figures, which will be down to 110 newtons. So our answer here was, I'll write down the full thing, 114 point, I think was 69, 169, sorry, 17 kilogram meters per second squared, which is newtons. Okay, remember we're up here, 1 kilogram meter per second squared equals 1 newton. Newtons, and I will shorten this because we can't set that accurate to 110 newtons. Okay, well, I might just do that because we're not too sure about it, and therefore we can say the force on the moon, their body weight on the moon is 110 newtons. Okay, and that's accurate to our two significant figures.